So here is our chapter review working on the practice test problems that I handed out to you in class. Okay, so solve for theta, where theta is between 0 and 360 degrees, and we need to round our answers to one decimal point. So when we're faced with equations, we need to go ahead and solve for the one function, in this case, number 1, tangent theta, and get that by itself first, just as if that were the variable. So I'm going to add 1 to both sides. So 4 times tangent theta is now equal to 1. Then I'll divide both sides by 4. So tangent theta is equal to 1/4. Now, after I've got that down to one function, one term, and it's solved for, now what I can do is take the inverse tangent of 1/4 and set that equal to theta. What I did was take the inverse tangent of both sides, so that would cancel out and I'd have just theta left. So that's something that I need to work on my calculator, making sure I'm in degrees, and I find the inverse tangent of 1/4. So for theta, I get 14.0 if I round to the 10th. Okay, now 1/4 isn't something that's on the table, so I had to use my calculator for this. But this isn't the only answer. Now, I need to figure out 14 degrees is a first quadrant angle where tangent is positive. Tangent is a positive 1/4. So I also need to figure out another quadrant where tangent would be positive. Remember, tangent relies on the x and the y coordinates. So if they're both positive, that's our first quadrant, but again, they could both be negative as well. So what I'll do then is take 14 degrees and add another 180 degrees to it, and my second answer is 194.0 degrees. In the second equation, number 2, the absolutely wrong thing to do is to divide both sides by sign, because then you would completely get rid of the signs and you would actually lose a root or lose some of your answers. So instead of doing that, let's subtract this sine theta from both sides. So I'll have sine theta cosine theta minus sine theta, and then we'll have 0 on the right side. Now what I can do is factor out sine, because sine is common in both terms. Terms are separated by subtraction or addition signs. So I'll take a sine out, and what I have left is cosine theta, and if I take out a sine theta from sine theta, I get minus 1, and we'll set both of those factors equal to 0 now. So sine theta equals 0, or cosine theta minus 1 equals 0, which is the same as cosine theta equals 1. That's something we can look at on our trig cheat sheet, what theta is. On the sine column, sine is 0 at 0 degrees, at 180 degrees, and 360 degrees, which I don't have to include. Cosine is positive 1 at 0 degrees, and at 360 degrees, which I don't have to include. So these are the two possibilities for theta. Okay, number 3 is kind of nice because it's already factored out for us, so we're just going to go ahead and set each of these factors equal to 0. So first of all, 2 sine theta is equal to positive 1. So sine theta is 1/2. 3 cosine theta is equal to positive 1. So cosine theta is 1/3. Now I know that a half is can be found under the sine column at 30 degrees and also at 150 degrees. But nowhere on the table do I have a 1/3 under the cosine column especially, so I'll have to go ahead and rely on my calculator for that. I'm taking the inverse cosine of 1/3, and I get 70.5 degrees. Now again, calculators are only going to give you one answer, and 70.5 degrees is a first quadrant angle. Where else would cosine possibly be a positive 1/3? Cosine is also positive in the fourth quadrant because it relies on the x-coordinate. So I'm going to take 70.5 degrees away from 360 on my calculator, and I get 289.5. So what I just did is 360-degree angle minus the acute angle 70.5. So I took 360 minus 70.5 to get 289.5. So those are my 4 answers for number 3. Okay, more of the same with this one, except we are now switching over to radians. I can tell that because x has to be between 0 and 2 pi. So we are in radians, giving answers to the nearest hundredth. So I'll go ahead and subtract 1 from number 4 on each side, so I'll have the cosine of 4x is equal to -1. Now I've already solved for cosine of 4x, and this is probably a little different than what you've seen before, but we'll work through it. And what I now need to do is take the inverse cosine of both sides in order to solve for 4x. Okay, so if I take the inverse cosine of both sides, that gets rid of the cosine on the left. The inverse cosine of -1, I can go on my chart and find that pi is the only place where cosine is a -1. Okay, now one thing I want you to just take a look at. This is what 4x is equal to. So what I want to do is figure out what x is, and it's not as simple as just dividing both sides by 4 and we're done. What we need to do is actually figure out 4 revolutions that are coterminal with pi. So I'll go and draw this down here. So here's pi. So here's the first answer. Now if I add another revolution to it, my second answer will be 3 pi. My third answer will be 5 pi, and my fourth answer, if I add another 2 pi revolution to it, will be 7 pi. Okay, I went out to 4 revolutions because what I'm doing then is dividing each and every one of these by 4, so it's going to find all possibilities between 0 and 2 pi by doing that. So now my answers are pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So maybe you're going to be faced with cosine of 2x. That just means you have to use 2 revolutions. Whatever answers or answer you get, you need to add another revolution to it before you divide and solve for x that way. Okay, let's move along to number 5. I'll switch colors here. And again, the last thing you want to do, you don't want to do, is divide both sides by tangent, because you're going to lose a root. So I'm going to get everything on one side by subtracting 3 tangent x from both sides. Set that equal to 0. Now what both of these terms have in common is a tangent. So if I take a tangent out, dividing each term by tangent, I get tangent squared minus 3 equals 0. And I'll move down here to the bottom here. So I'm setting each of these factors equal to 0 now. So tangent x equals 0, and tangent squared x minus 3 equals 0, which is the same as tangent squared x is now equal to 3. And then I will square root both sides so that the tangent of x is equal to, remember, plus or minus square root 3. Now we can solve for x. These are pretty simple because 0 and square root 3's are on the tangent column. So where tangent is 0, we have 0 radians, pi radians, and then 2 pi, which we don't have to include up here. Okay? And then we also have where tangent is positive or negative, square root 3. So I have on my chart pi over 3 is one of them, 2 pi over 3. The next one is 4 pi over 3, and then 5 pi over 3. So we have all of these cases for x, and those are the answers for number 5. Okay, number 6. Let's see, what should I do here? I'm thinking I want to get everything over on one side. What I'd probably want to do first is distribute the sign out. So I'll do that where I have space here. So I have sine x, actually that's negative, because we'll take it times a negative 1, plus sine squared x. Then what I'm going to do is subtract cosine squared x and move it over to the left side. And that's all set equal to 0. Now what I want to do is take a look at my identities to see if there's any way I can simplify this. Well, I thought I could take sine squared and cosine squared and they would add up to 1, but that's the problem. They're actually being subtracted and not added together. So that's not going to work using the Pythagorean identity that way, but maybe what I could do is rewrite cosine squared in terms of sine. So I'll have negative sine x plus sine squared x, and then minus, and then I'll substitute for cosine squared using the Pythagorean identity, 1 minus sine squared. That equals 0. I'm running off the page here. Okay, so I'm going to distribute that negative, so this will be plus negative 1 plus positive sine squared. So when I add like terms now, I've got 2 times the sine squared of x minus sine x, and then I've got that negative 1 hanging out here, and then that's set equal to 0, and now we're in quadratic form. Get rid of some of this. I hope this erases for you so you can see. So now this is in quadratic form, so I'm going to go ahead and factor. And I'll take a sign out and put it in front of the parentheses. 1 has to go in the back of the parentheses. Now I need to determine what would add or subtract to get negative sine x in the middle. Well, if I take a negative 2 sine x plus a positive sine x, that would give me the negative 1 sine x. Now that I've got that factored, I will set each factor equal to 0. So 2 sine x equals negative 1, so sine x is negative 1/2, and then over here I have sine x is equal to 1. So I'm going to solve it over here just so you guys can follow. So now what does x equal? I can look on my chart. These are nice easy numbers that are on my chart underneath the sine column. Where sine is negative half is 7 pi over 6, and at 11 pi over 6. And where sine is positive 1, that's only at pi over 2. So here are 3 answers for x for number 6. Finding the inclination angle for the line 8x plus 3y equals 10. That's where we need to use this formula, slope equals the tangent of the inclination angle. Okay, and again, an inclination angle, it seems like forever since we've talked about this, but anytime you have an angle or a line, it forms an angle when you measure it with the x-axis. So whether I have a positive slope or maybe a negative slope, I measure it up against the x-axis and get an obtuse angle, or maybe I get an acute angle. But either way, we've solved that by using m equals tangent alpha. Just remember that alpha has to be between 0 and 180 degrees. So if you get anything over 180 degrees, we need to plan accordingly. So first thing I want to do is get this in y equals mx plus b form so I can easily see the slope. So I'll kick 8x over on the right side and then divide everything by 3. Okay, I don't have to solve anything else really, I'm just interested in the slope. So my slope is negative 8/3. Negative 8/3 is equal to tangent of that inclination angle. What I'm going to do then is take the inverse tangent of both sides. So that's all gone, and we'll solve for alpha. Alright, now inclination angles are only measured in degrees, so make sure your calculators are set to degrees. And then we'll take the inverse tangent of negative 8/3. my calculator gives me a negative 69.4 degrees. Okay, this is a great example because alpha cannot be between or be a negative. It's got to be between 0 and 180. Let's visualize what a negative 69 degree angle looks like. So somehow or another this slope is doing something like this. That's probably where we're getting that negative 69.4 degrees. But what I'm really interested in is figuring out how I can figure out this obtuse angle going from the x-axis positively to find that obtuse angle. Just realize that lines form 180 degrees, so what I'll do is take this negative 69.4 and I'll add 180 degrees to it to get this remaining obtuse angle. And when I do that, I get 110.6. So that is what my inclination angle is. Okay, so I hope you had plenty of practice with the sine and cosine functions as far as graphing them. And in this case, we're supposed to write an equation in the specified form for the graph shown at the right. First of all, let's write this as a sine function. Sine and cosine look really similar. It just sort of depends on where we start our sine curve or cosine curve. Okay, remember a sine curve starts at the origin, at ground level, begins the hill, does the valley, and then back at ground level again. Cosine starts at the top of the hill, does the valley, and ends at the top of the hill. Okay, so we'll do sine first, and I'll do that in red. Okay, so it just depends on where your starting point is. Remember, sine starts at the ground level or at axis level, so we could either start it here, or we could start it here, or here. You know, there's many different ways we can do it. For this case, I'm going to start it right here, okay, at negative 1. So I'll start my sine curve at negative 1, so that means I had to shift horizontally over 1. So I need to make those changes in my equation. And then here's what the sine curve does. Hill, valley, and back up again. Okay, so by doing that, I am measuring the period if I go from negative 1 to positive 3. Okay, that's a span of 4. So the period of this function is 4. Amplitude's pretty easy to figure out because it goes up to positive 2, down as low as negative 2, and so amplitude is 2. Remember, you take the maximum minus minimum, divide by 2, you're going to get 2 in this case. Alright, so this is a y minus k equals a sine, or we'll get to cosine here, of b x minus h. That's the form you need to plug in. So we've got a lot going on. We know amplitude, we know period, and period is the same as 2 pi over b. So what we're going to do is solve for b so I can plug it up into this equation. Period is 4 in this case. So 4 is equal to 2 pi over b. If you multiply both sides by b, and then divide both sides by 4, b is pi over 2. So that's what I'm going to plug in for b here. Now horizontal and vertical shifting. Well, horizontal shifting is pretty easy to recognize. Here's our starting point right here, and we shifted that over to the left 1 unit. So this is going to be an x plus 1. Okay, but vertical shifting is a little different. If we take a look at this axis, okay, you don't want to see how high or low this graph goes, but you want to pay attention to ground level or axis. This axis is right on the money at the x-axis, so there was no vertical shifting here at all. So this will just be a y plus or minus 0, or just y. Amplitude is 2, and we said this was a sine curve. And b we figured out was pi over 2, so we're going to put that in front of the x parentheses. Okay, there are many other different ways you can write the sine function, just depending on where your starting point is. If it were here, the only thing that would change would be the x. This would be x plus 5, because we would actually be shifting over 5 units. Okay, So there's different ways you can do that. Or if we started at -3, well, it'd be a flipped sine curve because it would start at the bottom of the valley first. So there'd be a negative in front of the 2 sine. Okay, let me get rid of my mess, and let's start with cosine. I'll switch this over to blue. So cosine function, remember that's got to start at the top of the hill and end at the top of the hill. So I'm going to take the easy way. Here's the top of the hill right here, right on the y-axis. That's great. And then we will end at the top of the hill right here. Again, no matter how you measure it, period should always be 4. 0 to 4, period is 4, amplitude stays the same. So A's and B's are all the same. We just need to pay attention to vertical shifting, which again there is none. We're in cosine this time. Pi over 2 is the same. And now we need to take a look at horizontal shifting. Well, we started where x is 0. We started right on the y-axis here. So in this case there is no vertical shifting, and I'll just put an x there. Okay? Okay, this is kind of a fun one if in a sick sort of way, I guess. But you've got a giant Ferris wheel that's 60 feet in diameter, and the Ferris wheel completes a revolution every 5 minutes. We're going to graph this out, and hopefully you can see that period right away repeats itself every 5 minutes. Okay? So if I were to draw a curve, and this is going to end up being a sine or a cosine curve, we'll talk about that in a second, but period right away sticks out to me, and it's going to repeat itself every 5 minutes, okay? Alright, now it says we need to draw a graph of the height h. A person is above the ground t minutes, so this is x-axis is t minutes after boarding. Assume the closest a chair gets to the ground is 2 feet, so we can't be dragging on the ground, can we? So we are 2 feet above ground when we start. Now we have a couple choices. Either we can do a sine curve or a cosine curve. What do you think when a person boards? Are you going to start at ground level? Are you going to start at the top of the hill? Or are you going to start at the bottom of the valley perhaps? I would say bottom of the valley is where we're starting. Okay, so that's 2 feet above ground level is where the bottom of the valley is. Now, if the Ferris wheel is 60 feet in diameter, so the highest you're going to get is 62 feet because remember the bottom of the Ferris wheel is 2 feet above the ground. So we're going to go up as far as 62 feet. Okay? Alright, so starting at the bottom of the ground, and then we're going to reach the height halfway through, and then we are going to go back down to the ground and get off after 5 minutes. So this is looking like an inverted cosine curve where we're starting at the bottom of the valley, go top of the hill, and then bottom of the valley again. Okay, now it says in 11, write a function for height that a person is above the ground t minutes after boarding. Okay, so what it's really saying is we need to find the equation of this cosine curve. Okay, well, amplitude, 62 minus 2 is 60. Divided by 2, amplitude is 30. Period is 5. So period is 2 pi over b equals 5. Divide both sides by 5. Multiply both sides by b. I get that b is equal to 2 pi over 5. Okay? So I see that there is no horizontal shifting. We're starting right at 0 at the bottom of the valley, although we have negative cosine something. But we also have a shift vertically, okay? Ground level is not the x-axis anymore. It's going to be the difference between 62 and 2, halfway between there. So that's going to be right here, middle ground. Where is middle ground? We're going up how much? I know that this is a distance of 30, and this is a distance of 30 down to 2. So this has to be going up 32 units. So this is going to be y minus 32 is set equal to negative, amplitude was 30, cosine, remember it's negative cosine because we started at the bottom of the hill first, amplitude is 30, cosine b we found was 2 pi over 5, and just simply x because we did not shift it horizontally at all. Okay, now it says, how high above the ground is a person 13 minutes after boarding the Ferris wheel? Okay, well that means we need to plug in 13 in for x, and then we will solve for y. So actually we could almost just take this negative 32 and add 32 over here. Okay, so I'm going to go ahead and set my calculator and take 2 pi over 5, and I'll take that times, we're going to plug in 13 here, and then I'll take the cosine of that number, take that number times negative 30, and then add 32 to it. So what I get here is 3.21, and the decimal keeps on going, but it looks like after 13 minutes you are 3.21 feet above the ground at that point in time. So give the amplitude and period of each function and then sketch the graph. So here's our amplitude. Amplitude is 1.5. And this is b. This isn't period, that's just simply b. Remember, period is 2 pi over b. So in this case, period is now pi. Then it asks us to graph. Okay, so I'm just going to sketch this out as best as I can using this software. And we can go up to 1.5. I'm just going to mark this as 1.5. Down to negative 1.5. And then remember that this graph repeats itself after pi units. So I'm going to graph my action points. I got to quarter this up. Halfway between 0 and pi is pi over 2. This is pi over 4. And this is 3 pi over 4. You can see how it's going by fourths here, and just add the pi to it. This is a sine curve. So we're going to start at ground level. We are going to peak at the first action point, cross at the next action point, bottom of the valley at the third action point, and then we will go back up to ground level at the fourth action point. So here's what my sine curve is looking like, just like that. Okay, on to number 14. Y equals, we've got 2 kind of hanging out here, not really doing anything. It's not in parentheses with x, so I'm going to go ahead and subtract it from both sides, because what that really is indicating is a vertical change. Okay, then I have a negative in front of cosine, which is going to change something. It's actually going to flip it top to bottom. The amplitude is 3, I can tell already. So I'm going to write that down. Amplitude is 3. And period is 2 pi over this number, which is pi. 2 pi over pi is 2. So I'm going to go ahead and graph this. And I have action points here. Period is 2, so it's going to repeat the process after 2 units. Before I get too carried away, we've got that vertical shift 2. So that y minus 2 means we're actually going up 2. So I'm just going to make a dotted line here to show you what ground level is going to be at here for cosine. Okay, so here's 2, here's 1. I'm going to quarter this up. So this is 1.5, this is 1/2, and here we've got 0. So those are our action points when I got that quartered up. And then amplitude, we've got to go 3 above and 3 below this ground level dotted line, because that's what our amplitude is. And here's where it stops, right at 2. Okay, so if I go ahead and graph this, I'll use green. So cosine starts at the top of the hill normally and then ends at the top of the hill, but now we've got that negative in front, so that tells me we're actually starting at the bottom of the valley. We are going to cross ground level at the first action point. The next action point is going to be top of the hill. The next action point is crossing at the axis, and then we are down back at the bottom of the valley again at the last action point. So here's what my cosine curve is actually looking like. Okay, so it's the cosine curve like this, but flipped around because of that negative. Okay, here we are just simplifying expressions. I don't see any kind of identities I can use other than if I were to just rewrite this in terms of sine and cosine. So I'm going to rewrite secant as 1 over cosine, tangent, and I will write that as sine of negative x over cosine of negative x. I'll figure that out here in a second. Times cosine, that's already in sine cosine form. And I can see that these two are actually canceling. So now I have sine of a negative angle over cosine of a negative angle. If you were to look at your even odd identities, that's the front page middle of your trig sheet, it says that the sine of a negative angle, like we have up on top, can be changed to negative sine x, and cosine of a negative angle can be changed to a positive cosine x. Now this isn't quite simplified as much as you can because we've got sine and cosine, two different functions. I want to get that down to one term. Well, if I were to just leave it as tangent, okay, instead of converting it to sine or cosine, sine over cosine is tangent x, don't forget that negative out front. Now I'm down to one term, one type of function, and I would consider that simplified. So for number 16, again, we didn't do a whole lot with the cofunction relationships, but I'm just going to go ahead and use my trig sheet, that's really all I'm doing, to figure out cosine of 90 minus an angle. It says is the same as sine of that angle. Okay? And then I am going to take this times cosecant A minus sine A. Okay? If I take sine times cosecant, they're actually reciprocals of each other. This is the same as 1 over sine A. So if I took sine A times 1 over sine A, I'm just going to get 1. And then when I distribute sine A times negative sine A, I'll get a negative sine squared A. Well, we've got two terms, one function, yes, but we have two different terms here. I can simplify this further. I hope you recognize that that is the same as the Pythagorean identity, and I can rewrite it as cosine squared A. Now I'm down to one term, one function. Okay, for number 17, I might do this a little differently. There's a few ways you can do this, but one might be to rewrite everything in terms of sine and cosine. But what I'm going to do this time, I'm going to break apart this fraction. You see that they are both over the same denominator, tangent x. So I'm going to separate those two terms out and put them over the same common denominator, tangent x. So I just split apart the numerators, put them over the same denominator, tangent x. Okay? Now I know tangent x over tangent x would simplify to 1. Oh, and that should be cotangent. So when I have cotangent divided by tangent, okay, cotangent, and if I were to rewrite tangent as 1 over cotangent, and then when you're dividing by that fraction, I'm actually multiplying it by the reciprocal. So now I have cotangent times cotangent over 1, which is cotangent squared. And if I have a cotangent squared plus 1, my Pythagorean identities tells me that's cosecant squared. And now we're down to one term and one function again. For number 18, I have a cosine squared over 1 minus sine squared. Okay? What I would probably do is rewrite cosine squared, use my Pythagorean identity, and rewrite it as 1 minus sine squared x, and put that over the denominator. Now this is the difference of squares, so I can factor this out as 1 minus sine x and 1 plus sine x. And that's over 1 minus sine x. You can see that the 1 minus sine x's eliminate. They are now canceled, so now I have 1 plus sine x. There's no other way of doing this other than having the two terms, but yet I am down to the one single trig function in my expression, and that's as far as I can go. Okay, good luck on the test. Bring some questions if you have any. I am always willing to help.